Now we have one final speaker left before the lunch break, which is Valter Loll from Loll Consult.
So it's working? Okay. Thank you. So, my name is Valter Loll. I've been working with robust design for 35 years now, and I want to give you some examples of design guidelines for robust design using load strengths and design experiments. And it's all things that I've done personally, so it's not some make-up examples, it's real examples from real life. So another definition of robustness from the IEEE, the degree to which a system or component can function correctly in the presence of invalid inputs or stressful environment conditions. So that's another definition. I was once at a meeting at Nokia product development, big meeting, where the Nokia CEO said, I want you to be more creative, take more risk, work faster, work cheaper, and reduce the warranty cost with 50%. And everyone shouted, it's not possible. Well, I think it is possible, but not working the way we used to work. And this has something to do with closing the feedback loop. And if you close the feedback loop, here, what is it? Sorry? Yeah. Okay. That one. Okay. If you close the feedback loop from here in the field, it takes years to get the feedback. If you make system testing, it takes months. Integration testing, months. Module testing, weeks, maybe months. So the classical way of doing it is to do the test analysis and fix, test, make some changes, and launch the design. Now the V model, classical V model, shows this, but we can see that the feedback loop here is far too long. But if we work down here in detailed design, and we use some techniques of simulation and evaluation, we may come down to feedback of minutes to days. So that's what was my recommendation, that we would do that, move down here and focus on design guidelines and simulations. Now, Nokia decided to do something else. They decided to focus on test and quality control. And well, today we have seen the results of that. They, all the specialists which worked down here, they were fired or left the company, and the focus was up here. So my recommendation is to find tools that will allow you to work here. And which tools could that be? Design review, there's an international standard on that. FMEA, which will be discussed also here, there's also an international standard on that. Fault tree analysis, also an international standard. Designer experiments that I will come back to. Finite elements that we just saw. Tolerance analysis that has just been discussed. Load strength analysis that I'll come back to. Degree of freedom analysis, which has also been mentioned today. And Monte Carlo simulation. So that's just some of the tools that you can use in the detailed design. Now you will need to combine tools because you will not be able to make a total optimization of a big design today. That will not be possible. And using several tools means that you cannot have one key performance indicators as the top management want. You will have several, at least 6, I should think. We saw that number today, and I think that at least is what you need to have a good indication. It's amazing what you can do today with simulation. Simulating the drop of a mobile phone. So simulation, of course, is some very important tool to do this. For another tool is the Taguchi signal-noise ratio. Taguchi described that the signal is what the design parameters, the thing the designer can influence. The noise is the user and environment that the designer cannot influence. And then, as is usual in electronics, he optimized the signal-noise ratio measured in dB. Because if you have a strong signal with a little noise, you have a robust design. If you have a weak signal in a lot of noise, you don't have a robust design. And usually you will combine that with a design experiment, as I did here. It was a new design, which was the prototypes were tested and the results was not satisfactory. The design team discussed for weeks what the problem was and came up with 15 parameters, which I name here A to O, which they thought had influence on the problem that they had. I decided to use a fractional design, a Taguchi L16 design, to do the screening. I only had 3 prototypes, and I needed 16 test runs. So I had to modify the 3 prototypes to get 16 different prototypes. And that was done. We made the test during the weekend. And then on Monday, I could present the results all on this figure. So it's a lot of information that is put down here. We have the design parameters from A to O. We have the effect on each parameter from the x-axis and upwards. The higher the column, the stronger is the effect. We had 3 different function criteria, and we repeated the test only using 2 failure parameters or function parameters. So altogether, I had 5 results, and that means 5 columns. So going upwards, that's the effect that's on performance. Going downwards, I plotted the signal-noise ratio in dB. And based on that, I could tell the project team which parameters are important. And the important parameters are A, G, J, K, and O. So that's the important parameters. Then we could find the optimum, which is A2, G1, I2, JK, J1, K1, O1. Forget about the rest. They are not important for this problem. Another interesting thing is that the optimum performance also had the best signal-noise ratio, because you can see that we changed most of the factors, changed the sign between performance and the signal-noise ratio. So the most effective performance also gave the most robust design. So we were lucky, there was no trade-off needed. So that was a very efficient way of do the screening to find the critical parameters of this design. For tolerances, which has just been discussed, Of course, you can use the loss function of Taguchi, and you can see that the slope of the parameters variation in D has a lot of influence on the output parameters here, while the influence of L is less because less is more creating more variation in output, sorry, and D is creating less because it is steeper. And you can, if you have the design function, you can do that with a partial derivative as described by Morrison in his book. It's in the references. And it is like when you are skiing and you are standing on the mountain and looking down, which way should I take? The partial derivative tells you what the slope is when you are going down. And based on that, you can choose the tolerances which you need to tighten and find the tolerances that you can allow to be more loose. A special tool is the load strength, originally developed for mechanics, but also used today also for electronics. It's based on that the strength of a product will vary with the tolerances and variations in material parameters. And the load will vary according to the user, the climate, the environment, and things like that. And if there's an overlap between those two functions, you will have some failures where the load is larger than the strength. And you can calculate the reliability as this double integral. And when you know the reliability, you can find the failure probability because they add up to 1. Now, the general case of for example, Weibull distributed load and strength curves can be solved, for example, using the Weibull++ software. I had a thesis at the Danish Technical University, which showed that for a power transistor, the strength was Weibull distributed with a beta of 1.2 up to 1.8. That's close to log normal distribution. And the load had a beta of 1.4 up to 3.1, where 1.4 is more or less log normal, and 3.1 is close to being normal distributed. So you can solve the general case using the design software of Weibull++. If both curves are normal distributions, it's much easier because then you can use the safety margin, which is the mean strength minus the mean load divided by the square root of the standard deviation squared. And when you have the safety margin, you can look up the probability of failure in a log normal table. And if you have a safety margin of 2.3, it's 10 to the minus 2% failures. If you have a safety margin of 4.7, you're down to 10 to the minus 6 failures. And this is for one load, or you can say it's for a one-shot device. And so far, we are not looking into wear out and fatigue and things like that, but we'll come to that in a moment. A.D.S. Carter, which is a basic book on this theory, describes two cases where all real design will be somewhere in between. And besides the safety margin, he defined something he called load roughness, which is the standard deviation of the load divided by the combined standard deviations. So in case A, you have a constant load and a strength that is varying. Or you can say that the standard deviation of the load is much smaller than the standard deviation of the strength. He calls that case A, and the loading roughness is 0. In this case, the load is varying, but the strength has a much smaller standard deviation than the load. In this case, it's called case B, and the loading roughness is 1. It's easy to calculate for a one-shot device or population, because this small triangle is the probability of failure, and this small triangle is the probability of failure. But if you have more than one load, what will happen then? In case A, the reliability will be the same, because the weak items fail on the first load, and the rest will remain strong enough if we don't take into account wear out and fatigue. On the other hand, in case B, the reliability will go down because sooner or later you will have this big load which will make it fail. So you can tell what will in these cases, the development over time, what that will be. Now, for putting things into series, in this case, if you put things into series, the reliability will go down fast, because sooner or later you will use some of these weak items and it will fail. But here in case B, you can put things into series because they are all of equal strength. So if one is strong enough, they will all be strong enough. So usually, a case A is associated with mechanical things and case B with electronics. Not always so, but it's usual, the combination. You can see it here that now we are looking into fatigue and degradation. So the designer must, at time 0, make sure that there is a margin here between the load and the strength curve. And if we want to test for that margin, we can use the halt test to find out when it fails. So we can see if there are parts of the design which does not have the margin we need. And if there are some of these, typically it's 2 or 3 details in the design which is not strong enough, you just have to make them as strong as the rest. You don't have to make the whole thing stronger. You have the load spectrum here, and you can see after some time of degradation and fatigue and corrosion, the strength curve will meet the load curve, and that is the end of useful life. So we can now take into account the wear out. Then my designer will ask, how much margin do I need here? Tell me how much margin is enough. And Carter also was looking into that using his safety margin and his loading roughness. And if we plot the safety margin and the logarithm to the failure rate, we can see that we have 3 areas. Here the failure rate is too high. It's not useful design. Here it's too sensitive, not useful design. But if the designer places himself right here, you will have a failure-free design. And here's some of these curves from ADS Carter. And you can see that that depends on the safety margin and the loading roughness, and whether you have a single load or several loads. But these curves we saw in a thesis, again at the Danish Technical University, the approximation used by Carter and O'Connor, which have the same figures, are not quite precise, unfortunately. So more research is unfortunately needed. I used load strengths at Bang & Olufsen to design a moving mechanical part, because Bang & Olufsen needed urgently to detect the speed, the size of a record. And they did that by weighing the weight of the record. So we have here, we have an axis, and we have the torque around from the load of the record, from the strength of a spring, and a friction of a switch. So I had 3 distributions that I had to combine. And I did that using the general laws for combining uncertainties, made the load strength calculations, came up with a safety margin of 2.7, and from a table of the Gauss distribution, I found 0.36% failures, and we launched the product, and it worked fine in the market. So it was a good success. So you can use it, load strength, for dynamic calculations.
Valter, we just have a few minutes left.
Few minutes, okay. For screw towers, we made a designer experiment together with the designer, with the supplier of the screws. So we could optimize the parameters for and give design guidelines for a design tool. We had another problem at Bang & Olufsen with the flexible snap block, which should keep the printed wiring board into place. They broke because they have to keep it into place, but they also have to take the load when the customer was pushing the buttons. And we could show by simulation and calculation that we could not, with the tolerance of the PC board, be within the fatigue limits of the plastic parts. So what we did was we divided the function between a part which would just keep the PC board in place and a fixed stop which would take up the load, a very rigid stop. The Airbus did the same thing. They tried to make things stronger because they failed the load test. But once they did that, it became stiffer and they had cracks. So they had another redesign. I did this simulation for plastic parts using the load strength for different safety factors 1, safety factors 2, safety factors safety factors 2 and safety factors 10, and here 1.2. And I could calculate the percentage of failure for different orientations of the flow and in the plastic molding. So I could give design guidelines for how much design margin was needed. So conclusion, test analysis and fix is obsolete in my opinion. Robustness must be designed in. Designer experiment and signal noise ratio is useful. Tolerances by designer experiments and the loss function and partial derivatives is useful. Design guidance based on designer experiment and simulation is very useful. And companies should develop design guidelines, and also companies and consultants should develop design guidelines. Hope also universities would develop design guidelines. Load strength analysis is very interesting, very important, but more research is needed on how to estimate the load and strength distributions, and also the safety margin load roughness curves, where we need more information about the approximation of these curves so we can use them for design. So that was my presentation. Thank you very much.
Thank you very much. I know we're a few minutes over time, and I think everybody's hungry, but I think we should still have just 1 or 2 questions before we go to lunch, if anyone has some. Yeah.
The last point on your presentation was to do with the loading roofers.
Yes.
I think Carter acknowledged that there were some assumptions made in his numerical work in working out those curves. So there is a difference between O'Connor's, Carter's, and other people's.
Yes, there are.
Where you get fairly good probabilities per application of load. So there's also a condition that the underlying distributions of stress and strength are normal. And so there's, in your experience, when does that assessment need to take place? Because obviously load and stress can be a variety of different distributions. But those curves only accommodate normality.
No, the curves that I showed you also exist for other distribution, Weibull distribution. So these curves exist. But the thesis at the Danish Technical University showed that the approximation used by O'Connor, and I think also by Carter, is not precise. So we need to look more into that. So there is more research needed. In my opinion, the three basic authors within this field is A.D.S. Carter, Patrick O'Connor, and Professor Casey Sigolo at Tucson University. That's the three that I use.
Okay. We are 7 minutes over time, so I think we'll stop it here. Thank you very much, Valter.
Thank you. Thank you.
Now it's time for lunch, which will be from now on until 1 o'clock. And lunch is out in the foyer, and we'll meet here again at 1 o'clock. Thank you.